Welcome back to the Deep Dive. Today we're heading out into the cosmos. For a Science Corner Deep Dive, we're tackling what we're calling deep sky challenges, galaxies, cosmology, and reionization.
It's quite a topic. We're really looking at the immense challenge of figuring out how everything went from, well, the fairly smooth early universe to the complex web of galaxies we see now.
Exactly. And we've got some great material guiding us, a detailed review on cosmic star formation, brand new findings from JWST surveys like JADES and Pearls, and, insights into the core physics involved.
Our goal here really is to explore these hurdles. We'll touch on the tools we use, the observational methods, the theoretical puzzles that, frankly, keep us up at night.
I bet.
And crucially, what the newest discoveries, especially from JWST, are telling us about the universe's infancy and that key event, reionization.
Okay, let's dive in. You said it's a challenge. A big part of that seems to be how we model the universe. We've gotten really good at simulating dark matter, haven't we? The invisible stuff.
Oh, absolutely. N-body simulations, they're fantastic. They really nail how dark matter collapses under gravity to form these halos, which are like the scaffolds for galaxies.
Right.
But when you try to add the normal matter, the baryons, gas, stars, the things we actually see well, it gets orders of magnitude more complex.
So the visible stuff is the tricky part.
Yeah.
Why? What makes those baryonic processes so hard to simulate accurately?
It's just the physics is so much more intricate than gravity alone. You've got gas cooling down inside these dark matter halos. That's baryonic dissipation. It's messy, turbulent.
Okay.
Then how does that cold gas actually condense to form stars? That depends on local density, temperature, things we often can't resolve in big simulations.
Right.
And forming actual spectures, like spinning disks or those more rounded spheroids, another layer of complexity. Plus, you have stars creating heavier elements, metals, and spreading them around the galaxy and even between galaxies. Chemical enrichment.
So it's not just gravity pulling things together. It's all these localized, complex interactions.
Exactly. And that brings us to a really critical idea, feedback.
Feedback. Energy getting pumped back out into the system.
Precisely. Think about massive stars exploding as supernovae, or materials spiraling into a central massive black hole. These events release tremendous energy. That energy heats gas, pushes it around, can even blow it right out of the galaxy, these galactic outflows we talk about. And this feedback is absolutely crucial because it regulates star formation. It stops everything from just collapsing into stars all at once.
Okay, so if we can't simulate every star, every gas cloud, how do the big theoretical models handle this feedback?
Well, that's where we rely on what's often called phenomenological treatment, or more commonly, subgrid modeling.
Subgrid.
Yeah.
Meaning below the resolution of the simulation.
Exactly. In these huge cosmological simulations, you just can't resolve the tiny scales where feedback happens around a single supernova near a black hole. So we have to put in simplified rules, kind of like recipes.
Like if this happens, then assume that effect occurs.
Sort of, yeah. You insert rules that try to capture the net effect of that small-scale physics on the larger simulation grid.
Okay.
But the challenge is these subgrid models rely on parameters that are, well, poorly determined, as the review puts it. We don't always know the exact strength or efficiency of these processes from first principles.
And different assumptions give different results.
They can, yes. And sometimes you have degeneracies. Different combinations of parameters might produce similar-looking galaxies, making it really hard to figure out which physical process is truly dominant.
I understand this leads to some classic problems in simulations, like the overcooling problem.
It's a textbook example.
Yeah.
If your feedback isn't strong enough or implemented correctly, the simulations predict gas cools way too efficiently, forms far too many stars, especially early on. You end up with galaxies that are just too massive compared to what we actually observe. Getting feedback right across all scales is, well, it's a persistent headache.
Okay, so if simulating individual galaxies in detail is so tough, how do we actually piece together the history of star formation for the whole universe?
That's where we often switch tactics. Instead of getting bogged down in simulating every single galaxy perfectly, we take a more empirical approach. We look at the integrated light, the total emission from the entire population of galaxies across cosmic time.
By looking at different distances, effectively looking back in time.
Precisely. We observe galaxies at various redshifts, which correspond to different epochs, and measure their combined light output.
And different wavelengths tell you different things, right?
Yeah.
UV versus infrared.
Absolutely crucial. UV light typically traces young, hot, massive stars, so it's a direct probe of ongoing star formation.
Right.
But
Yes.
dust, always dust. Especially at higher redshifts, galaxies can be incredibly dusty. Dust absorbs that UV light and re-radiates in the infrared. So if you only look in the UV,
You miss a lot of the star formation.
you can underestimate it massively. So we use techniques to correct for this.
Yeah.
We look at the slope of the UV spectrum, or we compare the far infrared light to the far UV light to gauge how much energy was absorbed and re-emitted. Think of it like trying to see through smoke.
Makes sense.
Yeah.
And just finding a typical patch of sky is also a challenge. Cosmic variance you mentioned.
Yes, cosmic variance is a big one. Our deepest surveys, like the Hubble Ultra Deep Field, are amazing but cover tiny areas. You might happen to point your telescope at a region that's unusually dense or unusually empty, just by chance.
Skewing the average.
Exactly, especially at high redshift when structures were just forming. Wider surveys, like Cosmos, cover much larger volumes, so they average out these variations better, but they're usually not as deep. We saw this early on. Differences between the Hubble Deep Field North and South showed this effect quite clearly.
Right. Despite these difficulties, though, observations have converged on a pretty consistent picture of the overall cosmic star formation history, haven't they? What does that look like?
Yes, there's broad agreement. The universe's star formation rate seems to have increased rapidly at early times, maybe scaling something like inverse time cubed between redshift 8 and 3. It then hit a peak.
Cosmic noon.
Cosmic noon, exactly. Between redshift 1.5 and 2, when the universe was about 3.5 billion years old. That's when star formation was most intense across the universe. After that peak, it's been gradually declining down to the present day.
Interesting.
What's maybe a bit surprising is that the rate of star formation back at redshift 7 was roughly the same as it is locally today. Different kinds of galaxies dominating perhaps, but a similar overall rate per volume.
And how much stellar mass had actually built up by them?
Well, the total stellar mass density, all the stars packed into a given volume, has obviously been growing over time. It looks like it reached about half of its current value, somewhere between redshift 2 and 1.
So relatively recently in cosmic terms?
Relatively, yes. And looking back further, maybe only about 1% of all the stellar mass we see around us today was actually formed before redshift 6. It really emphasizes how much galaxy growth happened after the very earliest epochs.
And we can also track the buildup of heavier elements, the metals.
We can. We look at the cosmic metallicity. At redshift 2.5, the average metallicity of the universe was maybe only 1% of the sun's. Today, it's closer to 9% solar. Interestingly, the total amount of metals produced doesn't seem to depend hugely on exactly what kinds of stars formed first, the initial mass function, or IMF.
Okay. Now, galaxies don't just have stars. Most massive ones have these supermassive black holes at their centers. How do they fit into this growth picture?
The black holes.
Ah.
There's a fascinating link. Locally, we see this really tight correlation between the mass of the central black hole and properties of the host galaxy's bulge, like the stellar velocity dispersion, the M-sigma relation.
Suggesting they grow together somehow.
It strongly suggests their growth is coupled. And we can actually try to trace the growth history of these black holes across cosmic time, too.
How do you do that? You can't just weigh them directly at cosmic distances.
No, but we can use something called Sultan's argument. It's quite clever. It basically relates the total light emitted by actively growing black holes, seen as quasars over all of cosmic history, to the total mass that must have been accreted onto them. You sum up all the light to figure out the total fuel burned, essentially.
I see. And how does that history compare to the star formation history?
Well, this is where it gets really compelling. The derived growth rate for black holes seems to track the cosmic star formation history remarkably well, also peaking around redshift 2.
So they peak at the same time.
Roughly, yes. It suggests star formation and black hole growth are closely linked processes, perhaps feeding each other in some way, across most of cosmic time. Though, I should add, there are still some differences between various studies trying to measure this black hole accretion history, so it's not completely settled.
But the indication is strong. Coordinated growth.
That's the feeling. And remember feedback. The immense energy released when black holes are actively feeding the quasar phase, that's thought to be another major source of feedback. It could drive those galactic outflows we mentioned, maybe even shut down star formation in the host galaxy eventually.
Connecting it all back together. Okay, let's shift focus now to the really early universe, using the power of JWST. We're talking about the epoch of reionization.
Yes, a pivotal era. After the Big Bang recombination, the universe was mostly filled with neutral hydrogen gas, opaque to certain kinds of light. Reionization was the process where the first stars and galaxies produced enough high-energy photons to ionize that hydrogen, making the universe transparent like it is today. Probing this era has been a huge goal for decades.
And specific galaxies, these Lyman alpha emitters, or LAEs, are key probes here.
They are excellent probes. Lyman alpha photons are produced copiously in star-forming regions, but they scatter very easily off neutral hydrogen atoms. So if you see strong Lyman alpha emission from a very distant galaxy,
It tells you the path wasn't completely blocked by neutral gas.
exactly. It suggests either the gas within the galaxy allowed it to escape, or, more significantly for reionization, that the intergalactic medium along the line of sight was already largely ionized. Observing LAEs at high redshift is a direct way to map out the progress of reionization.
And JWST, with surveys like JADE's, is now finding these LAEs at incredible distances, beyond redshift 8.
It is. JADES has made some groundbreaking discoveries of LAEs way out there. And with instruments like NR-SPEC on JWST, we can finally study their properties in detail, their spectra, their kinematics.
So what are we learning about these very early galaxies from JADE's?
Well, a few things stand out. They're often quite bright in the UV, similar to slightly later galaxies, but their Lyman alpha lines sometimes show surprisingly small velocity offsets from the galaxy's own motion.
What does that small offset mean?
A large offset usually means the Lyman alpha photons bounced around a lot inside the galaxy before escaping, suggesting significant internal neutral gas. A small offset hints that the photons might be escaping more directly, maybe through cleared channels or from a very compact source.
Interesting.
They also show a huge range in how strong their Lyman alpha emission is compared to their other light, the equivalent width, and, critically, how efficiently that Lyman alpha actually escapes the galaxy. The escape fraction varies a lot.
Some are very efficient emitters.
Remarkably so. We're seeing escape fractions ranging from maybe 10% up to an incredible 72% in one case. That particularly efficient one looks very compact. Generally, these seem to be low-mass galaxies undergoing intense bursts of star formation with relatively low metallicity, which fits our picture of young, early systems.
And are they good at producing the ionizing photons needed for reionization itself?
Yes, that's another key finding. They seem to be very proficient producers of ionizing photons, significantly more efficient than the canonical values often assumed for early galaxies. So these types of galaxies could definitely play a major role in driving reionization.
Okay, so they make lots of ionizing photons, Lyman alpha is escaping. Does that mean JWST has solved reionization?
Huh. Not quite. In fact, this is where a major puzzle emerges. That LAE with the really high 72% escape fraction. For its Lyman alpha light to escape so effectively, it needs a very large bubble of ionized gas around it. Otherwise, the surrounding neutral intergalactic medium would just absorb the light.
How large are we talking?
The estimates suggest this ionized bubble needs to be about 3 physical megaparsecs in radius. That's the actual size at that time, not stretched by cosmic expansion.
3 megaparsecs. That sounds big for one little galaxy to clear out.
It is. And here's the rub. That required bubble size is much larger, like an order of magnitude larger in radius, meaning over 1,000 times the volume than what you'd expect based on the ionizing photons produced by all the other galaxies we can actually detect nearby.
Whoa! So this one galaxy needs this giant cleared space, but the visible neighbors couldn't have created it.
That's the implication. It strongly suggests there must be a large population of much fainter, currently undetected galaxies in that region, all contributing their ionizing photons to create and maintain this large bubble. We might just be seeing the bright tip of the iceberg.
Fascinating. So the faint galaxies might be doing most of the work.
It seems plausible, yes. And it's not just this one type of observation raising questions. Other JWST surveys, Pearls, CIRs, Glass, and just Deep, they're finding other unexpected things too. Galaxies with smooth disks way earlier than expected, these strange little red dots, galaxies that seem perhaps overmassive for their cosmic epoch.
Challenging the models again. What about just the number of galaxies seen at these early times?
At the very highest redshifts JWST is probing, like Z12.5, the number density of bright UV galaxies seems higher than what many simulations predicted. A bit lower down, say redshift 8 or 9, the numbers seem more consistent with previous Hubble estimates and simulations. But overall, the JWST results strongly support the idea that galaxies were indeed the main drivers of reionization, at least by redshift 8 or so.
Okay, so summing up, we have this broad observational picture of how stars and mass built up over time. JWST is giving us these incredible, sometimes puzzling glimpses into the very early universe and reionization. But it sounds like fundamental challenges remain.
Oh, absolutely. That's putting it mildly. While the observations are painting this increasingly detailed cosmic history, linking that back to a predictive, first principles understanding of the underlying physics is still a major hurdle.
And it really keeps coming back to those theoretical modeling difficulties you started with, the feedback, the subgrid physics.
It really does. Our current inability to accurately predict the cosmic star formation history from theory alone stems from this. It's partly the huge range of galaxy masses involved, but fundamentally it's the challenge of correctly modeling feedback from stars, supernovae, black holes processes happening on scales far too small to resolve directly in our large-scale universe simulations.
Which leads to those models being described as ad hoc, or maybe too simplified.
Sometimes, yes. They're often calibrated to match certain observations, rather than being truly predictive based on fundamental physics we fully grasp and can simulate from the ground up. Without getting feedback right, you inevitably face problems like overcooling, making too many stars too early in the simulations.
So progress requires both better observations and better theory and simulations.
Absolutely, they have to go hand in hand. Deeper observations, like from JWST, are essential. They provide the crucial data, the stringent tests that push our models, but we also desperately need breakthroughs in the modeling itself, better ways to capture the complex small-scale physics of galaxy evolution within a cosmological context. It's not just about matching numbers, it's about understanding the why.
And the discrepancies JWST is already throwing up are really highlighting the gaps.
They are. The higher than expected number of galaxies at Z 12.5, the early complex structures, this puzzle of the enormous ionized bubbles needed for some LAEs. These aren't minor issues. They strongly suggest our current models might be missing key ingredients or perhaps even fundamental aspects of how galaxies formed and interacted with their environment in the first billion years.
We've certainly journeyed far in this deep dive, from the nuts and bolts of simulating galaxy formation, tracing cosmic history, the role of black holes, right up to JWST, peering into the dawn of time and reionization.
It highlights just how vibrant this field is. These deep sky challenges show how much we've learned, but also how many exciting questions remain. The observations keep pushing us, revealing surprises.
It definitely feels like a revolutionary time in cosmology and astrophysics.
It truly does. A very exciting time to be working in this field.
So let's leave you, our listeners, with a final thought to mull over. Considering the surprising efficiency of some of these early galaxies in making ionizing photons, the puzzle of these huge ionized bubbles seemingly required around them, bubbles potentially much larger than the visible galaxies alone could create, and JWST finding galaxies with unexpected shapes and numbers at the earliest times. Could it be that the fundamental physics governing galaxy formation and their interplay with the gas between them way back in the universe's first billion years is actually significantly different or more complex than our current models capture?